Hi, this is Matt McCormick. I'm in the Department of Philosophy at California State University, Sacramento. My email address is mccormick@csus.edu. And this is the first of four lectures, short lectures for my inductive logic course, probability theory course. We are learning about Bayes' theorem. This is also associated with um, Introduction to Probability and Inductive Logic in Hacking's book, Chapter 7. So let's start an introduction to Bayes' theorem, part 1. What are we talking about? Well, Bayes' theorem is hugely important in modern science. Reverend Thomas Bayes, who lived in the 1700s, devised this theorem to show how new evidence could be incorporated in to update your current beliefs. So the idea is that this is a formal mathematical model. It's a rule. It's derived from the conditional probability rule, which we've been learning about in my course. But it's a rule that gives us a formal model to be able to have one belief. I've already got a belief and I've got a probability associated with it. I believe something to some, 80% probability. And then I make an observation, and Bayes' theorem allows me to incorporate that observation into my belief to figure out whether my belief is now strengthened or weakened as a result of the observation I've made. And that depends on the connection of the evidence or the observation to the hypothesis that I've got under consideration. So you can probably hear how general that is. It's not an exaggeration to say that Bayes' theorem is to probability what the Pythagorean theorem is to geometry. It is huge, it's foundational, it's really important, it's being used everywhere. It's now being used in AI research, evolutionary biology, economics, statistics, medical diagnoses, genetics, cryptography, wide range of other problem-solving cases. Every time you pick up your phone, you use Google Maps, or you use a search engine, Bayes' theorem is producing the answers for you. Someone somewhere has put that into a line of code and they're using it to give you answers, update beliefs with new evidence. Okay, so here's a formulation of it. I'm going to show you several different formulations of it. This is with A's and B's, and you'll recognize that it looks a little bit like the conditional probability rule, except it's conditionalized. It's got that in the right-hand side of the numerator, it's got something you wouldn't recognize. So that's Bayes' theorem. What's the probability of A given B? Well, it equals the probability of A times the probability of B given A over the probability of B. Okay, we're going to look at several different versions, and I'm going to start changing one of the things we'll do is we'll change these variables to be H and E, so you recognize what we're talking about, the hypothesis and the evidence, or the observation. Okay, so how do we get it? I'm just going to quickly show you the proof. It's a proof. We're not going to learn the proof in this class. I'm not going to demand that you do it. But proofs matter in epistemology, they matter in mathematics. And what's important here is that we can start with, as our first line in a formal proof, we can start with the conditional probability rule, which is that thing, which we've been working with in class. We've now solved lots of problems and done lots of work with that. We can take that, and with a few simple steps, we can derive that version of Bayes' theorem that I just showed you. So here's the first step. If I were to take line 1 and multiply both sides by the probability of B, I get that line. So look at that for a second. That means that the left-hand side of the equation is now multiplied by the probability of B right here. And if I multiply the right-hand side by the probability of B, what happens is that this probability of B and this one, they cancel out. So we get rid of the fraction, and we're left with this line. So two things have happened in this line. I've also flipped the order. So this probability of B is canceled out, and I flipped the order. But you can do that with an equation. Equivalence says that whatever's on the left-hand side is equal to whatever's on the right-hand side. Equivalence is symmetric, so we can flip it around. And this is what's known as the conditionalized multiplication rule. You don't need to worry about that for any other projects in our course. But now we can get Bayes' theorem, or at least the initial statement of it. How do we do it? We take this line 3 and go back to line 1. And notice that line 3 says that the probability of A and B, this left-hand side of the equation, is equal to this phrase on the right. So that means that if the probability of A and B occurs up here in line 1, which it does in the numerator, I can replace that top part with this part of line 3. So the right-hand side of line 3 now replaces the numerator in line 1 because we just proved in 3 that those two are equals. And when you do that, you're left with this. And this is the first statement of Bayes' theorem. And that follows by 1, 3, and substitution. There's other more technical ways to do it. There's other ways to derive it. But there's a quick and sketch or quick proof of why Bayes' theorem is true. If we think that the conditional probability rule is true, and we make 3 inferences that themselves are all legit, legal, and valid, and don't admit of any errors, then we know that this Bayes' theorem is true too. But again, we're not going to do formal proofs in this course. Okay, now let me bring your attention then to 3 different formulae. The first one here is the conditional probability rule, which we've been working with. And we can think of it this way. We're asking the question, what's the probability of A given B? That's the left-hand side. The answer, it's a ratio of the cases where A and B happen over the total instances of B. And we looked at a whole bunch of problems like that, and we've explored that. And you should have some intuitive understanding for that, even if you, and if you don't, you've applied it, and we've solved some problems. Okay, now we've also seen a proof now for the general version or general formulation of Bayes' theorem, which is right here. And this is the same thing as what I showed in the last slide, except instead of A and B, I've now got H and E. I can use any variables I want as long as I keep the order and I keep it all neat and equivalent. And the question now is, think of H as standing for hypothesis and E as standing for evidence. So now what we're asking on the left-hand side of this equation is, what's the probability my hypothesis is true given the evidence or the observation that I've made? And this is the answer on the right-hand side. So we might ask the question about the left-hand side, does my evidence confirm the hypothesis? The answer is it's a ratio. Is H true right here? Is the hypothesis true? We need to assign a probability to that. And also, it needs to be true that the evidence would produce would be produced by that hypothesis. That were it true, the evidence would come out like that. And then that's a ratio over the total number of cases or total probability of cases where the evidence gets produced. Okay, now that's going to be hard to sort of understand conceptually. I'm going to run through a bunch of examples that help unpack it and help make sense of it and try to make it more intuitive. Okay, now third formulation. This is called Bayes' theorem for two mutually exclusive hypotheses. And this statement of Bayes' theorem is equivalent to the general formulation of Bayes' theorem. But I'm not going to prove that for you. I'm not going to show it to you. There might be a proof of it in Hacking's book. I can give it to you in class if you'd like to see it. But you'll just have to take my word for it that this thing down here is mathematically equivalent to this thing right here. So these two formulations of Bayes' theorem are the same, or they're equivalent. But what's more important here is that in this Bayes' theorem for two mutually exclusive hypotheses, we're now dealing with a simple world where either the hypothesis is true or it's false. And we're just looking at those two exhaustive cases. We're imagining that it's either true or it's false, and that covers all the possible range of cases. So intuitively, it means something like, does the observation confirm the hypothesis? Well, that's a ratio. It's a ratio of the cases where E confirms H and H is true, over E confirms H and H is true, or E confirms not H, because it might happen that we might see that evidence with not H being true and not H is true. Okay, so that's kind of written in quasi-English. I'm going to do it more in English. I'm going to move back and forth from the numbers to the concepts and see if I can make that more and more intuitive. We've got a lot more to talk about to get there. Okay, so there's the statement of Bayes' rule for two mutually exclusive hypotheses. You will need to memorize that. You'll need to know that for our problems, the sorts of cases we're going to do, what we're going to do in class. And it's not that hard, actually. All you got in order to memorize it, all you need to do is you remember the first part, the probability of H given E, and you flip that around for the first part of the numerator, the probability of E given H, and then multiply it by the probability of H. So the numerator is not too hard to remember. It's just a flipping of the left-hand side of the equation. And then this whole thing, the numerator, gets copied down here at the bottom on the denominator, the left-hand side. So these two are the same. And the right-hand side of the denominator is the same too, except the h's have been changed to not h's. All right, so it looks like a lot of chicken scratches. It's very intimidating. It looks incoherent. There's the formula. You'll need to know it. I'll try to make it make more sense. Okay, so how to read it? Well, we've already learned how to read the given notion. That the question we're asking on the left-hand side is, what's the probability that my hypothesis is true given some observation or evidence that I've got? So you can think of some examples. What's the probability that your laptop was dropped given that it's broken? There might be some other causes. Maybe somebody stepped on it. Maybe it was vandalism. Maybe it was something else. What's the probability that you have a cold given that you have a sore throat, where a sore throat is your observation, your evidence? There might be other causes. Where in Northern California, there's lots of smoke, or you might have been shouting too much last night in a noisy bar. What's the probability that the game is rigged, given that you've lost so many times? Well, maybe there's some other reasons you're losing. Maybe the game is just, it's highly improbable that you'll win. What's the probability that the email is spam, given that it contains all caps and exclamation points? Maybe it's just your excited grandma who just got onto email and she's very excited and she's using all caps and exclamation points. So actually, that's a good example. On Gmail or on your email provider program, there is a bit of software that uses Bayes' theorem to make a decision about whether a new incoming piece of email is spam or whether it's something you might want to look at. And it can be trained, and it looks for things like all caps or exclamation points. Okay, so some more background to set this all up. This is also a statement of the same Bayes theorem, not for two mutually exclusive hypotheses. This is the original formulation. Now, in this statement, it's O instead of E, but it doesn't matter. And I want to use this to point out that that it will really help us to be able to refer to the different parts of the equation. These parts of the equation, the sides, the top, and the bottom, they have names. So the posterior probability, if you ever hear anyone talk about the posterior, what they mean here is the posterior probability is this left-hand side of the equation. It's the answer, it's the conclusion, it's the thing we're trying to find out about. And then the likelihood of the hypothesis, you've been hearing me talk about the accuracy of the test. The likelihood is this phrase right here. It's the left-hand side of the numerator. So think of it this way. The probability of an observation given a hypothesis. In other words, the probability that the hypothesis confers upon the observation. And I'll give you some examples in a minute where it makes it clearer what that means to flip the H and the O around, but it's exploring the strength of the connection between that observation and that hypothesis. How often, what's the probability that if that hypothesis was true, that it would produce those observations? What's the strength of that connection? The prior probability is also known as the base rate, and that's this thing over here on the right. It's the reasons, it's the grounds or the probability that we have for thinking the hypothesis was true from the outset, before we made our observation. So our prior probability is just H right here, and the posterior probability is this answer on the left. And what this equation does is folds in this new observation and lets me update my belief. The bottom, the denominator, sometimes gets called the unconditional probability of the observation. And we'll talk about that in detail. In particular, we'll talk about disconfirming cases in a minute. Okay, so let's make it intuitive, or try to make it more intuitive. Here's an example. What's the probability that she's mad at me given that she's not texting me back? So I look at my phone and I'm surprised to see that my wife hasn't texted me all day. Okay, well, what's going on? I need a hypothesis. What's my hypothesis? Well, maybe she's mad at me. That's a hypothesis that would explain the evidence. The evidence is the lack of texts. Okay, so written out in English then, plugging in the hypothesis and the evidence into Bayes' theorem for two mutually exclusive hypotheses, we're really asking this question. What's the probability she's mad given that there are no texts? Well, it equals this. So the probability that there's no text given she's mad times the probability she's mad over that great big messy denominator. Okay, so there's really four things we need to know here to be able to answer the question, to plug in some numbers and come up with a value. So the prior then, prior to my observation of no texts on my phone, the prior question, the prior probability is, well, are there any independent reasons to think she's mad? What's the probability that she's mad? Maybe it's high, maybe it's low. Maybe she's got nothing to be mad about. Maybe she has something really serious to be mad about. Who knows? The likelihood is asking this question. Well, in general, if she were mad, is that the sort of evidence that would result? If she's mad, does that mean she stops texting? Because some people, maybe instead of not texting, they text more when they're mad. It's not that they don't text, they text more. So the absence of text wouldn't suggest that they are mad if that's one of those people, right? So somebody, you can imagine somebody being all along the spectrum, right? You can imagine some people who their likelihood is very high. When they're mad, they don't text at all. For other people, you can imagine their likelihood being very low in this case. When they're mad, they text a lot, so it doesn't work. It doesn't fit, doesn't match. So the two other things we need is the probability that she's not mad, and that's just the prior minus the prior. And what are the other reasons, or what's the probability you might see that evidence and she's not mad? That is, what are the other non-mad reasons she might not text? Maybe her phone's dead. Maybe she didn't pay her bill. Maybe she's out of cell service. Maybe she's busy. Maybe she's not getting my text for some reason, right? There's a whole bunch of other reasons besides being mad for that sort of outcome, that sort of possibility. So we got to think about those and fold those in to this observation to figure out whether or not this observation supports the conclusion that she's mad. Okay, so she's not texting. Is she mad at me? There's the equation. So think of it this way. I'm going to try to explain it conceptually, then we'll stick some numbers in there. If there's no real reason, there's no prior reason to think that she's mad, and she's not the sort of person who goes silent on text when she is mad, then the numerator is going to be really small. If we assign small values to those two numerators, maybe they're 0.2 or maybe they're both 0.1. If we could put small values on those, she's probably not mad, and she's not the sort of person who goes silent when she is mad, then the numerator is really small. Okay, that's important. And if there's a lot of non-mad reasons that she might go silent on text, then the denominator would be large, right? So what's the result if the numerator is small and the denominator is large? Well, that means we've got a fraction that is bottom heavy. That's a fraction. If the numerator is small and the denominator is large, then the fraction is small. I mean, think of 1/4 or 1/6 or 3/11 or 1/50, right? Those are small numbers. So that means we're giving a low answer to the question, what's the probability she's mad given there are no texts? And when we plug in these low values, then it looks like, or the low values for the numerator, then the conclusion is probably not. That is, if the numerator is small and the denominator is large, then the answer to the question is probably not. That is, if the probability that she's mad given no text is low, and you should just chill out, she's not mad, something else is going on. On the other hand, if the probability that she's mad is high, there's some prior reason, and if the only reason she ever goes off text and is that she is mad because she keeps her phone charged and she never leaves it and she has good service, well, now we get a different story. Here's what I mean. Imagine a situation where you've got some prior reason to think that she's mad. Before you look at your phone. Maybe you had a fight, or maybe something happened. Who knows? If there's some prior reason you assign a high value to that, then that means in this numerator we've given a high value here, and suppose that this person is the sort of person who, when she gets mad, she stops texting, whereas she never lets her phone run down, and she is rarely out of service, and there aren't any other very frequent reasons for her going off a text. So now we've got a high value in the numerator and a lower value in the denominator. So the fraction goes up. So it goes up to 7/8 or it goes up to 9/10 or something. That is, the probability is getting higher and higher. Answer to the question, what's the probability she's mad given there's no text? And it looks like the probability is creeping higher in that kind of scenario. Okay, so here's some numbers. Here's the same problem. Let me see if I can make sense of it. So suppose that we assign a prior probability, a low one. You can't think of anything she might be mad about, so you just put a 0.1 on this initial prior probability that she's mad. And suppose that she's not the sort of person that stops texting when she's mad, so you give the likelihood a low value too. You give that a 0.1. Furthermore, the probability that she's not mad then is got to be 0.9 because this is two mutually exclusive hypotheses. She's either mad or she's not. That's the way we're kind of carving up the world just to keep it neat. So if the probability that she's mad is 10%, then the probability that she's not mad has got to be 90%. So that means that this not mad is 90. And suppose that she rarely stops texting for any other reason. Suppose we assign this value 0.9 to the probability of no text given that she's not mad. Suppose that that never happens. She rarely stops texting for any other reason. So you put a 0.9 value on that. Okay, so now I've just made up these values. I've just made up a scenario where you assign those values. That's okay. That's just to kind of motivate this idea that if the numerator comes out small and the denominator comes out big, then we get a low fraction and an answer that's very low probability. So when you plug in those numbers, 0.1 and 0.1 up here and here, and then down in the denominator, you plug in 0.1 and 0.1 and also 0.9 and 0.9, and then you do the math. You multiply those through. The answer you will get is 0.01219. That is, there's a 1% chance that she's mad. She's probably not mad. This is a very low answer. So we tried to set up to try to answer the question. I observe there's no texts. So I asked myself, what's the probability she's mad given that there's no texts? And I've inserted some values and I come up with the answer, well, 1%, really low, given these values that I've inserted into Bayes' theorem. All right, so that should start helping us make sense of this notion of the fraction of the ratio. Okay, consider the opposite sort of case. So consider the case where we've got a high prior and a high likelihood. That is, so it's the very same scenario. And suppose you just had a disagreement with your friend on email or on text, and you figure there's a better than even chance that she's mad. You've got some other reasons. You've got a prior that's fairly high. You put a 60% on that. Oh yeah, she's mad, I think. I already think. Some other reasons led me to think that she's mad. And furthermore, suppose, different than our previous case, this is the sort of person who typically drops off a text when she's mad. She ghosts you and she stops. So you say, yeah, that's pretty common. What's the probability of no text given she's mad? 90% of the time, when there's no text, it's because she's mad. So you put a 0.9 on that. And furthermore, the converse, what's the probability she's not mad? Well, that's 1 minus this probability, so it's 0.4. And what about the probability of no text given that she's not mad? Well, suppose there are cases where sometimes her phone dies or something else happens. So you say you put that at 0.3. And you may have noticed already, you may have wondered, why are these not adding up equal to 1? They don't. It's a very complicated story here. These two values will add up to 1 when we're doing two mutually exclusive hypotheses. So these will always add up to 1, but these need not. And I'm not going to explain that anymore. I'll just sort of warn you that they don't. Okay, so now when we plug in those values, we get this equation, we get this result, and we get a 0.82. So what's the question we answered? What's the probability she's mad given that there's no text? In this scenario, given that we had a high prior and we had a high likelihood, now we're at an 82% probability that she's mad. So it looks pretty good. This information, I mean, think of it this way, is that our prior probability of her being mad was 0.6, and then we make a new observation. We observe no texts, and that has now led us to revise or increase our estimation of her being mad to now 0.82. So this observation has bolstered or increased our confidence in the conclusion that she's mad, now to 0.82. So it's moved it up. And Bayes' theorem has given us the mathematical way to fold in that information and the reliability of the likelihood of the information, and then incorporate it, and then revise and update our belief. Okay, so here's what we've done then. I've just set out to sort of roughly explain conceptually that Bayes, how Bayes theorem works. So Bayes proved Bayes theorem in the 1700s, and it can be derived from the conditional probability rule, and we saw quickly how you could do that. Here's the general form of Bayes theorem. The way it's usually, you'll see this on t-shirts and the way this usually gets stated. Here's the way you state Bayes theorem for two mutually exclusive hypotheses, and you should get to where you can recognize that and reproduce that at will, so you know what it is. And we've learned that there's names for some of these parts of the theorem. So the prior probability is just the probability of H, and it goes on the numerator up here. The posterior probability is the thing on the left-hand side of the equation. The probability of E given not H is the probability that we will see this evidence when the hypothesis is false. That's the other sorts of cases, like maybe she's not texting because her phone's dead, or because she left her charger at home, or because she's really busy, or she's out of self-service. Those are other non-mad reasons for having the observation that we made, and that gets incorporated into the denominator right here. These are the disconfirming cases. This is where confirmation bias often throws us off when we're trying to figure these things out. And what we're learning now, and what I hope I'm starting to explain, is that this equation is a ratio that lets us make observations and figure out if they confirm or disconfirm a hypothesis. And we're learning that if the prior is low and if the likelihood is low, then the numerator is low. And if the denominator is large, then the answer comes out low, and vice versa. And we're going to start looking at cases and looking at how different base rates affect the output of Bayes theorem and how different likelihoods affect the output of Bayes theorem. But that'll all be in the later sections of this discussion. All right, so that's the end of part 1 of my introduction to Bayes theorem. Tune in to part 2 to start seeing some more concrete examples, and we'll start unfolding.